Welcome to the Deep Dive, the show where we distill complex research into clear, actionable insights. If you've been watching the AI landscape, well, you know generative models are moving at an incredible speed.
Just warp speed, really. Hard to keep up sometimes.
Totally. And today, we're diving deep into something really interesting. Diffusion Language Models, or DLMs. Now, you've probably heard tons about autoregressive models, the GPTs of the world.
Right, the dominant players for a while now.
But DLMs are emerging fast as this really powerful alternative, very compelling stuff.
Definitely worth digging into.
Our guide for this journey is a really comprehensive survey paper, a survey on diffusion language models. It's from researchers at the Vila Lab, MBZ, UAI, and Tsinghua University. Fantastic overview.
Yeah, it's a great synthesis of where the field is and where it's going.
And our mission today for you is pretty simple. Cut through the jargon, unpack the core ideas, the unique advantages, what makes them tick, and, what the future might hold. Basically give you a quick way to get up to speed on this exciting field.
Sounds good. Let's do it.
Okay, let's jump right in. So imagine text generation that isn't just super fast, but also really smart about context, nuanced. That's kind of the promise of diffusion language models.
Right. The survey really highlights how they generate text differently in parallel.
Parallel, yeah. Using this iterative denoising process. And the upshot is often a huge speed up, several times faster than the traditional autoregressive models.
Which is a big deal in itself, but what's really compelling, I think, is that this speed doesn't necessarily mean sacrificing performance.
Exactly. They're hitting comparable results to the big AR models, but they have these built-in advantages, right? Like understanding context from both directions.
Bidirectional context, yeah. And giving you much finer control over the output.
Which makes them super interesting for a whole range of NLP tasks, and even mixing text with other things like images, multimodal stuff.
For sure. That's a really exciting direction.
So maybe to really get why DLMs are making waves, we should quickly touch on the current champs, the autoregressive models, the AR models.
Good idea. So AR models, the ChatGPT, GPT-4, they generate text sequentially.
One token after another, like building a sentence word by word.
Exactly. They predict the next token based on all the previous ones. And they scale incredibly well, handle tons of tasks.
No question they're powerful, but that step-by-step process, it's their main bottleneck, isn't it? Especially for speed.
Precisely. Inference speed is the big limitation because it's inherently sequential. You can't predict the 10th word until you've predicted the first 9.
Right, and that's where diffusion comes in with a totally different angle.
Exactly. Diffusion models, you probably know them from generating amazing images and videos. Stable Diffusion, Imagen, Sora.
Oh yeah, those are everywhere.
Their core idea is fascinating. They learn to reconstruct clean data, like an image, starting from pure noise.
Like sculpting from static.
Kind of. They gradually remove the noise over iterative steps to reveal the final image. And the key thing is, they can work on many parts of the image or data at the same time, inherently parallel.
Okay, so parallelism is the superpower there. How do you apply that to language, which feels so sequential?
That's the million-dollar question DLM researchers tackled. It led down 2 main paths initially. First, continuous DLMs.
Continuous?
Yeah, like the early diffusion LM. They map the discrete tokens, the words, into a continuous space, think embeddings, and then do the denoising process there in that sort of smoother mathematical space.
Okay.
But more recently, the focus has really shifted towards discrete DLMs.
So working directly with the tokens themselves.
Exactly. Defining that diffusion process, that noising and denoising, directly in the token space. Think of it almost like corrupting and then fixing a sequence of words. Early work like D3PM and then things like Diffusion BERT really push this forward.
So if AR is like writing a sentence word by word, diffusion is more like starting with a blurry sentence and gradually bringing it into focus.
That's a pretty good analogy, actually. Refining the whole thing iteratively.
And what are the big wins? What advantages do DLMs really offer over those traditional AR models?
Well, the advantages are pretty significant, and they stem directly from that core mechanism. First off, parallel generation. This is the big one.
Generating multiple tokens at once.
Right. Instead of one by one, they can predict and refine many tokens simultaneously during that iterative denoising. This means potentially massive boosts in inference speed, throughput.
That speed up alone feels transformative for real-time interaction.
Absolutely. Imagine chatbots, coding assistants, much more responsive. Second, they naturally handle bidirectional context.
Because they see the whole sequence at once during refinement.
Exactly. They're not just looking backward like an AR model. They can use information from both the left and the right of a token when deciding what it should be. This leads to, more nuanced understanding, better generation quality, especially for tasks needing that wider context.
Like filling in missing words in a sentence, maybe?
Perfect example. Or tasks that need to blend information from different sources, like text and images.
OC speed, context. What else? You mentioned refinement.
Right. Iterative refinement. That step-by-step denoising process isn't just about speed. It's also like a built-in quality control.
How so?
Well, the model can sort of lock in the easy parts, the high-confidence predictions, early on, and then spend more refinement steps on the trickier, more uncertain parts of the sequence. This often leads to higher quality, more coherent text.
Almost like self-correction.
Kind of, yeah. And this ties directly into another advantage, controllability.
Being able to steer the output more precisely.
Exactly. Because they operate on the whole sequence and refine it, you can condition them more easily on specific structures or target certain positions.
Yeah.
Think tasks like text infilling or generating text that has to follow a strict template.
And you can guide them too, right? Like with style or topic.
Definitely. Techniques like classifier-free guidance, which became really popular in image diffusion, work very well here, letting you precisely control aspects of the output without needing a whole separate model to judge it.
So speed, better context, iterative quality improvement, and fine-grained control. That's a compelling package.
It really is. And maybe one more point, this shared denoising framework seems naturally suited for unified modeling across modalities.
Bringing text, images, maybe other data types together?
Potentially, yes. The core idea of denoising could, in theory, apply to different kinds of data represented digitally. We're seeing promising steps towards models that can handle text and images within the same framework.
That sounds like a huge leap. How is this playing out in the research landscape? What trends does the survey point out?
Well, the survey definitely highlights that shift I mentioned, from the early continuous DLMs towards the discrete ones. That seems to be where most of the momentum is now.
Okay.
And we're seeing larger scale models emerge, things like Dream, Diffalama. These are often built on top of existing large AR models, adapting their knowledge.
Adapting pre-trained models, that makes sense for efficiency.
Yeah. But also models trained from scratch, like ELIDAE 8B. And this one's a big milestone. ELIDAE 8B showed performance comparable to ELIDAE 3AB, a similarly sized state-of-the-art AR model.
Wow, okay, so they're really catching up in terms of raw performance at scale.
It seems so. And it's not just academic anymore. The survey notes growing industry interest too, with models like Mercury from Salesforce and potential components within Google's Gemini family exploring diffusion techniques.
Fascinating. Okay, so we have the why. Let's unpack the how. How are these things actually built? You mentioned discrete DLMs are popular.
Right. Within discrete DLMs, a really common approach, especially for the larger models now, is the masked DLM paradigm. Think of models like LED here.
MACT, like masked language modeling in BERT.
Sort of similar intuition, but used differently. For training, yes, it learns by predicting masked out tokens in a sequence, using cross-entropy loss, just like many other language models. But the inference, the generation part, is where it gets really interesting.
How does that work?
You start with a sequence of entirely masked tokens, basically a blank slate of the length you want. Then, iteratively.
The denoising steps.
Exactly. In each step, the model looks at the current sequence, mostly masks at first, and predicts all the tokens. Then, based on how confident it is about each prediction,
It reveals some of them.
precisely, it unmasks the tokens it's most sure about, maybe the top 10% or some fraction based on a schedule. The rest stay masked, or might even get remasked if confidence was low for the next round of refinement.
So it gradually fills in the blanks, focusing its attention.
Exactly, until all the masked tokens are replaced with actual predicted words.
Okay, that makes sense. So what about training these models? Is it completely different from training, say, a GPT model?
Not entirely different, but there are key nuances. Let's talk pre-training first. As I mentioned, a lot of recent DLMs actually leverage weights from pre-trained AR models.
Like Dream 7B and Diffalama.
Right. They adapt those existing powerful models. It's a way to sort of jumpstart the process and benefit from the huge data sets those AR models were trained on.
Smart. But some are trained from scratch.
Yes. Like LADI 8B. Requires significant compute, of course. And interestingly, for multimodal DLMs, some actually initialize from image diffusion models, like DDIT or MUDIT, trying to port that visual understanding over.
Wow, okay. Diverse starting points. What about fine-tuning? Like for specific tasks?
Supervised fine-tuning, SFT, It's pretty similar conceptually to AR models you train on instruction following datasets, question-answer pairs, etc. But there are some efficiency challenges.
Because of the masking.
Yeah. During training, only the masked tokens typically contribute to the loss calculation. That might only be, say, 50% of the tokens in any given training step. So learning can be less efficient.
How do they deal with that?
There are strategies like Levita's complementary masking, which tries to ensure that across different training steps, all token positions get used for learning effectively. Also, there's a bit of a train-inference mismatch sometimes in how the masking is handled, which needs careful management.
Okay, that makes sense. Now, a big question for any language model today is reasoning. How do DLMs handle complex, multi-step reasoning tasks? Traditional chain of thought seems inherently sequential.
That's a critical point and a really active area of research. You can't just do step-by-step reasoning when your generation process is parallel.
So what's the alternative? Parallel reasoning.
Essentially, yes. Researchers are exploring ways to parallelize the reasoning chain itself. Early ideas like diffusion of thought, DOT, tried to refine intermediate reasoning steps in parallel.
Okay.
More advanced approaches like diffusion chain of lateral thought, DOT, are pretty clever. They use things like an unmasking policy module to decide which parts of the reasoning chain to reveal and refine when, and even use reinforcement learning based on the final outcome to optimize the whole multi-step reasoning process. It's less like a linear chain, more like exploring possibilities laterally.
That seems complex but powerful if it works. What about learning from preferences like RLHF for AR models?
Great question. Adapting reinforcement learning, specifically policy gradient methods and preference optimization, like DPO, to DLMs was a challenge.
Why is that?
Because standard RL techniques often need the exact probability of generating a sequence, the log likelihood. And for DLMs, calculating that precisely is really hard or intractable because of the parallel non-sequential generation.
Okay, so how do they solve it?
They developed clever workarounds and approximations. Methods like SIPO, Diffu-GRPO, Uni-GRPO, and VRPO find ways to estimate or work around the need for the exact log likelihood, allowing them to apply these powerful policy gradient or preference optimization techniques. This means DLMs can be fine-tuned based on human feedback or desired outcomes, like we see with LEA 1.5 using VRPO.
Very cool. Okay, so they can be trained, fine-tuned, even handle reasoning in their own way. Let's switch to inference, making them run fast and efficiently in the real world.
Absolutely crucial, and this is where a lot of engineering ingenuity comes in. The core advantage is parallel decoding.
Generating multiple tokens per step.
Right. But you can optimize this further. Techniques like confidence-aware decoding. Fast DLLM is a good example. Look at the model's confidence scores. They might only unmask the, say, top 5% most confident predictions in a step, allowing for many fewer steps overall.
So faster convergence to the final sequence.
Exactly. Fast DLM will report up to 27.6x speedups doing things like this. There are other strategies too, like adaptive parallel decoding, APD, slow-fast sampling, and even speculative decoding adapted for diffusion, like SpecDiff, also getting significant speedups. It's all about maximizing throughput.
Makes sense. And you mentioned the unmasking strategy itself is important.
Hugely important. The specific policy, how you decide which tokens to unmask, how many, and whether to remask on certain ones drastically affects both the final quality and the convergence speed. Models like LADA and DREAM have their specific schedules. And some newer work, like RAMDM, allows remasking tokens that were already decoded.
Going back and fixing things even after they seemed final?
Sort of. It adds flexibility, allowing a smoother trade-off between computation cost and output quality. You can decide how much refinement you want.
And what about guidance? Controlling the output precisely.
Yeah, guidance is key for controllability. Classifier-free guidance, CFG, is the dominant technique here, borrowed from image generation.
How does that work without a separate classifier model?
It's a clever trick. During inference, you basically run the model twice per step, once conditioned on your guidance, like a topic or style prompt, and once unconditionally. Then you nudge the output slightly away from the unconditional prediction and towards the conditional one.
So you use the model's own understanding to steer it.
Exactly. It lets you control the generation, make it stick to a topic, adopt a certain style without needing that extra classifier. And people have used it for really fine-grained control, like Dingo enforcing text generation that matches specific regular expressions.
Wow. Okay, speed-ups from decoding strategies, clever unmasking, guidance. What about pure efficiency, like memory and compute?
Big focus area. Researchers are adapting techniques proven in AR models. One is the key value, KV cache.
Right. That speeds up attention in AR models by reusing computations. But how does that work with DLM's bidirectional attention?
It's trickier but doable. the context isn't fixed like in AR generation, but techniques like block diffusion, fast DLMs dual cache, or DKV caches delayed caching find smart ways to cache and reuse relevant KV pairs across steps, still yielding significant speedups again, sometimes over 20x.
Okay, adapting KV caching. What else?
Feature caching. This goes a step further, caching not just the KV pairs for attention, but other intermediate activations within the model's layers across the denoising steps. Techniques like deep cache, DLLM cache, free cache report even bigger speedups, up to 34x by reusing more computation.
So caching at different levels. Any other major efficiency tricks?
Yes, perhaps the most dramatic is step distillation.
Distillation, like training a smaller model.
Similar concept, but applied to the steps. The goal is to train the model, or a variant of it, to achieve the same result but in drastically fewer denoising steps. Some approaches, like DLM-1, aim to generate the entire sequence in just a single forward pass after training.
One step, from mask to full sequence.
That's the goal. And if successful, the acceleration is potentially enormous. Yeah. The paper mentions up to 500x speedups in some experiments. It's a very active research direction.
Mind-blowing speed potential there. We started this talking mainly about text, but you hinted DLMs are moving beyond that.
Absolutely. The multimodal and unified approaches are really exciting. Handling multimodal inputs is becoming common.
Like feeding an image along with a text prompt?
Exactly. Models like Galata V or Levita use vision encoders to map image features into the same kind of embedding space the text uses. This allows the DLM to understand visual context for tasks like visual instruction following or image captioning.
So understanding multimodal inputs. What about unified generation?
That's the next frontier. Truly unified models aim to represent everything, text, images, maybe audio, code, as sequences of discrete tokens.
Tokenizing images.
Yeah, using techniques like VQ-VAE to turn images into codes. Models like MLDay, Unidisk, Fudoki, Mudit are exploring this. They try to build a single DLM that can process and generate across these different modalities seamlessly using the same core denoising process.
A universal translator and generator for data.
Kind of. We're also seeing interesting architectures like Dimple's autoregressive then diffusion training, or DIT's dual branch transformer trying to unify generation and understanding across modalities.
It's fascinating how these technical ideas translate into actual uses. What are some standout applications?
Well, they're being applied to many conventional NLP tasks. Classification, summarization like diffusum, translation, style transfer, they perform well, often benefiting from the bidirectional context.
But where do they really shine, perhaps differently from AR models?
Code generation is a really promising area. Writing code often requires thinking ahead, planning structures. It's not strictly linear.
So the DLM's ability to see the whole picture and refine iteratively fits well.
Exactly. That global planning and iterative refinement seem very well suited. Models like Diffucoders show strong results, and commercially, Salesforce developed Mercury Coder, a large-scale DLM for code, reporting up to 10 times speedup over highly optimized AR coding models while maintaining quality.
10 times faster coding assistance, that's huge for developers.
It really is, and the applications go even further into some really cutting-edge scientific domains.
Like what?
Biological and scientific applications. This is super exciting. DLMs are being used for things like molecular optimization, designing new molecules with desired properties, guided by text descriptions.
Wow.
And also de novo protein design.
Yeah.
Models like TransDLM, ForceGen, DPLM2 can generate novel protein sequences intended to fold into specific structures or perform certain functions, sometimes even co-generating the sequence and its predicted 3D structure.
So designing new drugs or materials at the molecular level using diffusion.
That's the potential, yeah. It really shows the versatility of the diffusion paradigm beyond just language or images.
Okay, this all sounds incredibly promising, but, every cutting-edge tech has its roadblocks. What are the big hurdles, the challenges DLMs still face?
Definitely. The survey lays out several key challenges. One of the most fundamental is the parallelism performance trade-off, sometimes called the parallel decoding curse.
The curse? Sounds ominous. What is it?
Well, we talked about the benefit of generating tokens in parallel. But the curse is that if you sample each token's identity somewhat independently during those parallel steps, you can get inconsistencies. The classic example, imagine your training data has lots of ABAB. An AR model easily learns this pattern. But a DLM, sampling position 0, 2, 4, potentially at the same time as 1, 3, 5, might see A and B as equally likely at each position individually.
And end up generating something weird like AA, BB.
Exactly, because locally at each position, A or B seemed fine, but globally it's incoherent. This issue can really hurt generation quality, especially if you try to use very few denoising steps to maximize speed. It's a tough balancing act.
That's a deep challenge. What else?
Infrastructure is a practical one. The ecosystem around AR models, think Hugging Face transformers, optimized inference engines like VLLM, is incredibly mature.
Right. Lots of tools, easy deployment.
Yeah. For DLMs, that mature, open-source, highly optimized infrastructure is still largely missing. Researchers often have to build more custom tooling, which slows down adoption and deployment.
Makes sense. Technical debt, almost.
Sort of. Then there's long sequence and dynamic length generation. DLMs are typically trained on fixed-length sequences. Getting them to generalize well to much longer text or to generate text where you don't know the final length in advance is still challenging.
Why is that harder for them?
Part of it is how they're trained, but also the standard bidirectional self-attention mechanism they use can become very computationally expensive for very long sequences. The cost can grow cubically with sequence length per step, which is a scalability bottleneck.
Ah, the dreaded n-cubed complexity.
Exactly. And related to that is overall scalability. While a lot of 8B is impressive, the largest public DLMs are still way smaller than the biggest AR models, which are in the hundreds of billions or even trillions of parameters.
So we haven't really seen if DLMs can scale to those massive sizes effectively yet?
Not broadly validated, no. Proving they can maintain their advantages at truly massive scale and doing so efficiently is still an open research question.
Okay, so performance trade-offs, infrastructure gaps, length limitations, and scaling questions. Those are significant hurdles, but what's the path forward? What are the exciting future directions?
The field is moving fast to address these. Improving training efficiency is key, maybe exploring hybrid architectures that blend AR and diffusion ideas, or finding better masking or objective functions.
Making them cheaper and faster to train.
Right. And for inference efficiency, there's huge interest in quantization and binarization, making low-bit DLMs that use much less memory and compute power.
For running on smaller devices, maybe.
Exactly. Or just making large deployments more feasible. Similar goals for applying pruning and distillation techniques, basically compressing the models without losing too much performance.
So leaner, meaner DLMs. What about capabilities?
Pushing towards truly unified multimodal unified reasoning is a major goal. Not just handling multimodal inputs, but performing complex reasoning across text, images, audio, etc. in a deeply integrated way.
The universal data reasoner.
That's the dream for some, yeah. And one area the survey points to as largely unexplored but potentially very impactful is developing DLM-based agents.
AI agents using diffusion models, how would that be different?
Well, imagine agents that can leverage DLMs' strengths, that bidirectional planning, the iterative refinement, the potential parallel action generation. It might lead to agents that are more flexible, more adaptable, maybe better at exploring complex state spaces compared to purely sequential AR-based agents. It's speculative, but exciting.
Very interesting possibility. Okay, let's try to wrap this up. What's the big takeaway here?
I think the main message from the survey, and from what we're seeing, is that diffusion language models are rapidly maturing. They're not just a theoretical curiosity anymore.
Right, they're becoming a genuinely compelling, high-performance alternative to the established autoregressive models.
Yeah, exactly. They bring unique strengths to the table, that inherent parallelism for speed, the bidirectional context understanding, the iterative refinement for quality, and the fine-grained controllability. Plus, this exciting potential in multimodal and scientific domains.
The foundational ideas seem solid, and the engineering is catching up fast to close performance gaps and boost efficiency.
For sure. Now, challenges absolutely remain: that parallel decoding curse, the infrastructure needs, scaling. These are real hurdles.
No silver bullet yet.
Not yet. But the sheer pace of innovation detailed in this survey is remarkable. It strongly suggests a future where DLMs play a really significant role, complementing or even competing with AR models in many areas.
That shift towards parallel generation could really change how we think about building and deploying language AI.
It could. It offers a fundamentally different set of trade-offs and capabilities.
We've covered a ton of ground, but honestly, we've only scratched the surface of what's in that survey paper for anyone listening who wants to dive even deeper.
Yeah, the researchers have put together a fantastic resource on GitHub. It's an awesome DLMs repository.
Onto DLMs, okay.
It collects papers, code, other resources related to diffusion language models. A great place to stay updated. We'll make sure there's a link in the show notes for you.
Perfect. Well, hopefully this deep dive gave you some real aha moments and armed you with some valuable insights into this incredibly dynamic field of diffusion language models.
Yeah, hope it was useful.
Keep learning, keep exploring the frontiers of AI, and we'll catch you on the next deep dive.